Good morning, ladies and gentlemen, and welcome to the third in our series of webinars designed to help new and existing teams be prepared for the 2021 Solar Car Challenge. I'm excited to have these opportunities to help keep the momentum moving because there are so many people who had started building cars and were slowed down because of pandemic limitations. But we think we're going to be able to have a race next year. We want to help you be prepared. By the way, some of the topics we're discussing will be discussed in greater detail in our new spring series of webinars. So I encourage you to take a look at those. That calendar of events will be posted this weekend. I'm excited. We've got great presenters today. Beginning, our race deputy director, William Shee, is going to talk to us about electrical engineering for building a solar car. And this will be followed by some real practical experience from people from the Okemos Solar Car Racing team. Will Jones was a former captain of this Okemos team, now studying engineering at Michigan. Eric is a captain of this team, Eric Andachek. So we're glad to have both of these outstanding young men here talking to us about the significance of telemetry and data gathering. Remember, we're not just a pedal to the metal type of car program. We are involved in helping you develop strategies so that you can best make use of the energy that's coming into your system. And you do this when you know what your car is doing and can discuss it with a strategy group back on the race pit. So to start us off on today's program, let me introduce you to William Shee, Deputy Race Director. William?
Thanks, Doc. I'm going to talk about electrical engineering, but before, just want to, for all those who are on the call, if you have questions, please feel free to just type them into the Q&A and we will get to them as we go along. So let's get started. Okay, so we're going to talk a bit about battery technology, electrical systems, and safety issues. And so let's talk through what an electrical system in a solar car looks like. You know, the full chain from how you get the sun's power all the way to actually getting your car moving goes through a series of major components: the solar array, maximum point power trackers, batteries, motors and motor controllers, and then we'll talk a bit about the rest of the electrical system as well. So let's start with the solar array. You have really two design options for how you're going to put that in your solar car. You, of course, can put a flat solar array, and that makes it really easy to put together because you don't have to worry too much about shadows, especially if you go wing over body design. And then you don't have to worry about the sun hitting your array in different ways and getting different amounts of energy. You need more planning for that. Now, you know, a flat solar array can be done sort of, we call it within body as well, where you cut out a section for the cockpit and then you have your solar array around there. There are some considerations there you have to decide in terms of shadowing and the like, and so something to consider there. A curved array, though, has some advantages because it gives you the flexibility to design your solar car with aerodynamics in mind, right? You're basically putting that curved array onto a more aerodynamic body, which means that you have some areas of angle between your solar cells. Now, you know, solar cells are brittle, and so when you flex them, if you flex it too much, they can start developing micro cracks, which affects the efficiency of your array. Likewise, you know, mounting to it, if you have a flat array, you can just put some bars, mounting brackets in place, and you're good to go. Normally, when you're looking at a curved array, you'll need to deal with sort of a thinner layer with adhesive to lay it down onto your solar car. And then, as we talked about a little bit, the angle of the sun is important. So if you have a curved array, as with the car that you see there, you'll have a part of your array that's getting more power because it's aiming towards the sun, and then you have another part that's away. And if you were to wire these in series together, you're really going to bring the power that you get from those solar panels to the lowest common denominator. So you have to plan out one side versus the other side and make sure that there's zones set up for that. So not only do you have options for how you lay out an array, you have options for the type of array that you want. You have sort of pre-made choices, either a commercial panel or specialty panels. So a commercial panel is something you can just get as if it is something you can buy for your house. They're pretty thick, sturdy things that are meant to be outside forever. And so you have a pretty strong metal bracket. You have a pretty thick piece of glass on top, and it's very reliable. You can just almost toss it around and won't have an issue with reliability there. Whereas there are some specialty panels that you can get. They're all, those are pre-made as well, that you can order that are more lightweight. Some are flexible. Some have just a thin layer of encapsulation, and so it brings the weight down. Some have some encapsulation that have some type of prism to them to try to sort of focus some of the energy into the solar array. And so that is definitely a nicer option for teams if they have the ability to, I guess, pay more for them. And SBM Solar is one of those companies, and they do both pre-made, and you can customize your order through them as well. Now, of course, you can go even further and just get some raw cells and lamination. So you can buy specific, raw solar cells and, design the array the way you want. You can say, I'm going to have a car like this. I want strips of 2 by 6 cells of this number of panels, 4 by 3 for other ones. That gives you the most customizable way of doing it in terms of you don't waste any space. You can tell them, I want the panels of this size, and I can fill in my entire allowable space. Whereas pre-made panels that you get off the shelf, you're just limited by their size, right? Now, being able to cut them into the right strips and optimize the locations of them can also maximize your power and reduce drag because you can lay them in the right place on your solar car. And one of the places that you can go for that is Suncat Solar out of Arizona. They can get some fairly high efficiency cells and then encapsulate them and laminate them for you, but at a fairly high cost. So certainly as a first-year team, that's something you probably don't want to consider. Now, if you want to save costs, there's another option. You can build it yourself. You can actually go and buy, solar cells raw, and then you can wire them up and solder each of the cells together. I did that in my first year racing. At the time, there weren't so many options out there to buy these prefabricated lightweight panels. And so we actually went and bought, a pack of cells and soldered, leads on the top and then leads on the bottom, and essentially make a set of solar cells into a panel in series. The learning curve is very steep there, right? Let's say this, when we did it, we broke about 20% of the cells. So you have to account for breakage. It's hard to find raw solar cells, but if you were part of our last webinar, you'll note that Joel Pitts from Greenville, they are going to be creating their own panels, and they just contacted SunPower directly and got a set of cells. So it can be done. And the way you do that by doing a do-it-yourself array, you can get the advantages of the custom array where you can design it where you want without the cost of doing that.
William, can I add something in here?
Yes.
I'd like to share a personal experience on this. Back when we had the old Winston Solar Car team, we had too reached that point where we wanted to try building our solar array. We were attempting to drive in the 1999 World Solar Challenge across Australia. So we bought $6,000 worth of individual solar cells, tabbed them, put them on the car, and found out it didn't work. We had not taken the time to learn how to properly tab those cells, and the currents didn't flow properly. The picture on the left shows how these people at St. Thomas Academy were doing this. We didn't do it as good a job as they did. So we ended up 6 weeks before having to put the solar car on an airplane to fly to Australia. That 6 weeks in advance, we had to take a paint scraper and scrape off $6,000 of solar cells and start over again. That was an absolute nightmare. What a great learning experience. What an improvement in the learning curve. But you need to do your research in advance.
Yeah, certainly. That could be a very expensive mistake, right? And one of the neat things that both our team did and as you can see, St. Thomas did, is that you sort of make a jig out of it. If you want to do it yourself, is you put the cells into a form where you know that the cells are properly aligned all the time, and then you run a lot of practice cells. So when we bought raw cells, you can actually get a set of practice cells and practice soldering the leads on, but still very expensive mistakes. And you can see on that slide on the right, basically mistakes that were made, and they have to go and break it and vacuum it out. So not something you might consider for first year, but there are ways to improve your efficiency through that. So those are the options for solar array. So let's move on to the next part of the system, the maximum point power trackers. So maximum point power trackers are simply a device that converts your solar array voltage to your system voltage. And the idea is not as simple as, oh, let me just hook up the solar array to the batteries, because there is that difference in voltage and it just doesn't take. And so you need to have something that's designed to convert that power. Now, you might consider, okay, why not just have some type of static DC-DC converter that can translate that voltage from another voltage? The benefits of having a maximum point power tracker is that a solar cell has certain characteristics with regard to voltage and current. Based off of the voltage that you have, you get a drop off in the current right at a particular voltage level. And so this is a particular curve for a solar panel that normally is about 72 volts, right? And so you can see the voltage down there is starts dropping off at that point. If you think about how a solar cell produces energy, and the energy is basically a calculation, the power is the current times the voltage, you really want to maximize the product of that current and voltage. And so how do you do that? If you look at a straight horizontal line, most of that part is just going to increase your power. But at some point in what we call the knee, it starts dropping off, and your maximum point power is really somewhere on that knee, where you can maximize the product of that current and voltage. And these devices, maximum point power trackers, does that for you. It actually puts the solar cells into the optimal position on the IV curve to give you the most power. So some of the considerations when you choose your power tracker is, do you want to get a buck or a boost power tracker? Most power trackers are basically one or the other. They can either take a high array voltage and bring it down to your system voltage. That's called a buck power tracker. Or you can have power trackers where you have low input array voltage and bring it up to your system voltage. That's a boost power tracker. So you have to decide, okay, how do I want to design my solar array, and how do I want to, what is my system voltage, and get the appropriate power trackers. The other thing to consider is the power trackers are really rated for a particular voltage. So there's a lot of power trackers out there that support 48 volts or less. So if your system voltage is 48 volts or less, you've got the world of options available to you. So something to consider when you choose what batteries and motors you use is, do I have a power tracker that supports that? Once you get above 72 volts, you really just have one option. You have the AERL power trackers. There might be others out there that the college teams use, but for the most part, if you get above 72, that's really where you're going to go. Third consideration is your current or power rating. The power trackers have a certain rating for how much current it can take in or how much power it can take in. And so it can only convert a certain amount of power. And so if you have more than what the power trackers can handle, you have to break up your array into smaller pieces, and that will allow you to have power trackers that handle that. And then efficiency, not usually a consideration, but there are power trackers that run 98, 99%, so they're really, really efficient. But you might look and make sure that if you had equal options, efficiency and of course cost could be some considerations for you. With regard to choices, I briefly talked about AERL, but they have designed essentially a solar car specific power tracker called the Raisbeck 600B. The 600 stands for the 600 watts that is able to convert in terms of power. And as I said, if you're above 72 volts, that's what you get. Nomura is this red one down here. It was something that Joel Pitts showed as well in his stuff. You can see the size of this is very small and very light. And you can see the coin that's in there that shows the scale of that power tracker. And so it's a lot of solar cars in the university level certainly use that type of power tracker. But looking at the specs, the output voltage is only 34.5. So teams have to do some special design in order to get it to the voltage that they need. Of course, that's the standard power tracker. They do make custom ones for the voltage that you want. So that's some other thing to consider. But most teams, I think, will go with things like a Midnight Solar or an Outback Power, these larger grid type of power trackers, or a Jenison tracker is a bit smaller there. And those are a bit more robust in terms of their conversion. It gives you some, if you can see, there are some telemetry outputs there that you can look at as well. And so those are definitely great options. And I believe even when some teams had trouble with some of these power trackers, the manufacturer actually came out to the race and helped them debug it. So lots of good support for things like that. And then I said, DC-DC converters, don't do this. You might be tempted to say, let me save some costs, buy some really cheap DC-DC converter and say, well, my solar panel has a nominal voltage of 38, and I'm running a 48 volt power as system voltage. And so let me just convert the two and we're good. But as I showed you on the graph on the IV curve, that's basically just going to select a particular voltage and keep it there for your input. And that means that you lose the ability to squeeze out more power from your solar panels. It's just not, you basically waste the purpose of the very expensive solar cells that you have on your car. Okay, so moving on from, we took the power from the array, we converted to the system voltage, and so let's take a look at batteries. Choose carefully. It's something that you have to look at, you get what you pay for. There are a lot of fairly cheap batteries out there, but they don't really serve the purpose. Before we get to considerations, I would say that for first-year teams, if you go out and buy a standard automotive battery, that's not going to work well for you in a solar car. Solar cars essentially have a large range of the battery it uses. It drains as you run the solar car, and then you drain it almost all the way down to the bottom potentially, and then you go and charge back up to the top. Automotive batteries, standard ones, are meant for staying up at the charge level, and then you just use it to start your car, which will take it down a bit, and then you charge it back up. So most of the time in an automotive battery, it's meant to be fully charged. So what you want to look for is a deep cycle or marine battery. Now, when you look at the decisions that you want to make, you have to consider what voltage do you want to run your car at. That also matters because in terms of your motor selection, you may have some limitations in terms of voltage, but the higher you can run your voltage, the less current that you have to run it. As I said, power is a product of current and voltage, and so the higher the current at the same power, you're going to get less current. And what does that mean? It means you can run less thick wiring, right? If you run, a 12 volt, motor, which we definitely don't recommend, you're going to basically be in double-aught, triple-aught wiring. Whereas if you're looking at least 48 volts, you can run something like a number 4 welding wire or something like that. The other thing is capacity. How much weight do you want to carry? We allow for 5 kilowatt hours of capacity, but do you want to run all of that in your solar car? Do you want to take it up to the to the maximum capacity? Because you have to, the more batteries you put in the car, the heavier it will be, and that will affect your performance because of the friction forces that you put on the car. How much energy can you get at that weight? So you want to start looking at energy densities and optimizing the number of battery packs that you have for that capacity. The other thing would be, can your solar panels recharge the battery pack? If you got a really huge battery pack, but you have some fairly inefficient solar cells, if you calculate the amount of time that you have in the day to charge on a particular race day, you may never get to recharge your battery pack. So that essentially means that once you start discharging your initial charge, you're just going to be carrying dead weight for the rest of the race. So it's something to consider there. And then you might have other considerations for a road race versus a track race, because as you know, if you're running on a road race, you're going to have ups and downs on your track. And so when you have ups and downs, you're going to have enough battery to be able to go up hills and use up a lot more energy there. Whereas a track race, while there's some gradual up and down because of the way the Texas Motor Speedway is laid out, certainly the grade is a lot less. And so some of the considerations there. Our rules require that you do not exceed 5 kilowatt hours in your capacity. And essentially that is, kilowatt hours could be calculated as amp hours times voltage times, of course, the number of batteries that you use. And so when you look at battery capacity, they tend to advertise that in terms of amp hours. And so you have to calculate that to a kilowatt hour rating by multiplying that by the nominal voltage. For lead acid batteries, you have to do that at a 20-hour discharge rate. The faster you discharge, the less capacity that you have, sort of the nature of the battery chemistry. And some battery manufacturers provide the capacity at a different discharge rate, sometimes 18, sometimes 24. And so when you compare batteries and your selection, you want to make sure that you're doing it with the same discharge rate so that you can compare apples and apples. So with regard to capacity, you want to look and say, if I got one of those sun extenders that are on the right there, they're 84 amp hour batteries at 12 volts. So you start multiplying things out. And so 84 amp hour batteries, 4 12-volt batteries, that equates to 4 kilowatt hours of capacity total. And that combined weight is about 230 pounds. So there's a question that came in with regard to supercharging. So I will say the question is, does supercharging factor in the maximum kilowatt hours? I will say that our rules prohibit supercharging in the sense of your voltage cannot exceed 16% of nominal for the battery. And so you wouldn't be allowed to supercharge. Having said that, we do calculate the voltage based off of the nominal voltage of the battery spec, right? So any particular battery will have a spec that says it is that voltage. That is the voltage that we use to calculate your capacity. Now, we know that a 12-volt battery in terms of nominal voltage is tends to be essentially dead at 12 volts or at 12.5 volts. So when fully charged, not when supercharged, but when fully charged, it really sits more at a 14.4 volts. And so we calculate the capacity at 12 volts, but you could be running 14.4 volts in your system, per battery when fully charged, and that's okay. And again, if you have any other questions, please fill it out in the question and answer, and we'll answer it as we go along. In terms of battery selection, for lead acid batteries, you have to look at Puchert's number, and it's not very well advertised nowadays. They just tend to give you a capacity rating, but certainly you can start looking for data sheets with the appropriate graphs. And Puchert's number is essentially the capturing the equation of charging and discharging. The idea is that in a lead acid battery chemistry, the faster you charge a battery, or the faster you discharge a battery, the less power you get out of it. And that gets worse by the higher Peukert number. So if you were to have an 84 amp hour battery that is shown in the last slide, you would say, okay, at a 20-hour discharge rate, I'll have 84 amp hours. That doesn't mean that when you discharge it at a 1-hour rate, as we would do in a solar car, or 1 or 2 hour discharge, you're not going to get 4.2 amps out of it. It just doesn't work because of those battery chemistries. So you want to be conscious of that in your battery selection, that the closer to 1.0, the better. And essentially, that's the benefit of lithium chemistries, is that essentially it is a 1.0 type of equation there. Finally, we talked a lot about battery specs and the selection based off of what manufacturers advertise. Don't rely on that. Rely on that only for selection of the battery. But once you buy the batteries, different batteries, because of chemistry, have different capacities based off of what they are. And so you want to test your batteries and see how much can these batteries actually hold. And so you can see the St. Thomas Academy built this testing rig with, I don't know if you can still get incandescent light bulbs anymore. Certainly you can't do that in California, but you want to get something that can take a lot of load and put those in there and run them in series. And then you can calculate, okay, I turned on this number of light bulbs for this number of watts for this amount of time, and the battery, will last this amount of time. And so then you can characterize which batteries are better versus worse, and knowing that you might buy more batteries than you would need because you might want some spare in case something happens during a race, you want to select your highest performing batteries for running in your car. And so this is part of the data collection that you do even before you start running the car. You should be doing this in your lab. So let's talk a bit more about lithium batteries. They are permitted only in the advanced or cruiser division cars. And instead of looking at 5 kilowatt-hour capacity at 20-hour discharge rate, it's simply calculated at 1C. And that's a pretty standard way of describing things in terms of lithium batteries. There are different types of battery chemistries for lithium. There is a lithium-ion battery. Those are the types of batteries that you might see on the bottom, the individual cells. They do have higher energy density, which means that you get more power for the weight that you are using. But it has a lower discharge rate, meaning it's really designed to be discharged at a 1C or 1 times the capacity rate. And so that's a consideration you have the trade-off you have to do, right? Whereas if you were to use a lithium iron phosphate or that type of chemistry, you might get a lower energy density, 90 to 120 versus a 150 to 200, but it supports a higher discharge rate, 1 to 25C, and it has better thermal and chemical stability. And so a lot of cars, at least in our race, certainly are moving to that type of lithium iron phosphate that you can see on the top half of that slide. It's sort of easier also for teams to incorporate because they look sort of like a standard car battery. They just have terminals on either side, and they've sort of just built up the batteries within the box, essentially, that it comes in. Whereas individual cells, you're going to have to wire up lots of them in series, because each lithium ion battery will probably be about 3 volts, and you just sort of add them all up. Advantages of lithium-based chemistries, of course, is a better charge and discharge efficiency. And we talked about that. with the Pickard's number is that you can discharge without losing that capacity. And of course, they're lighter. Even the difference between lithium ion and lithium iron phosphate, the energy density is much, much higher than a lead acid chemistry. One of the things, though, you need to be aware of is if you decide to choose lithium-based batteries, you must have a battery management system to protect the car. Essentially, these type of batteries could be essentially set on fire based off of overcharging. There might be some other things that happens for over discharge or temperature issues. And so you need to get a battery management system that will monitor those things and provide a cutoff if those conditions occur. And you'll see that on these prismatic battery here on the screen, there are these little circuit boards that are on each of those, and they are essentially inputs to a battery management system that will help protect the batteries. So certainly something that advanced or returning teams will want to look at, but I think it's something neat to be able to optimize your car with. So we took the array, we took the sun's power, went through the array, converted to system voltage using a power tracker, and we stored the energy in a battery. So what's next? Let's drive the car. And so you have options there with regard to motor selection. A lot of the motors that are sort of entry-level motors are either brushed or brushless electric motors. The brushed motors, which is sort of the top, especially this top left here, the advanced DC motor, is fairly inexpensive. It's quite a workhorse of a motor in terms of its reliability, but it is fairly inefficient compared to some of the other options that you have. What's neat about these is it's fairly easy to wire. You just hook up, positive and negative essentially, and say, there it is. The advanced DC motor or some of the other motors certainly is an option that entry-level teams might want to do just to be able to get their car moving. Now, if you want to move further in terms of cost and efficiency, you can definitely go towards a brushless motor. And the difference between a brush motor and brushless motor is simply that there are some magnetic brushes within the motor that turns that cause the from the electricity coming in to cranking the motor that's used either by magnetic brushes or a brushless system. And so typically in a brushless electric motor, they do it in a 3-phase. And so there's a little bit more complexity, but not too much. Okay, the motor efficiency curves is something that you want to look at in terms of motor selection. The motors are really designed to be run at a particular RPM. And so you'll see two different motor efficiency curves there. The one on the right is from the ME0909 brushless motor. And you'll see that there's an area of maximum efficiency that's there that runs, somewhere on the order of, 2200 RPM to 2000 RPM. And so if you can gear your car to run at that RPM, then you get the most efficiency. What teams tend to do is to overestimate the cruising speed of their car and then gear it to, let's say, I want to run 30 miles per hour all the time. And then they get to the race and they go, you know, I can't run it at 30 miles per hour all the time because of the amount of energy that I get. So I end up running at 15, 10 miles per hour. And that gets you to a fairly low RPM, which gets you decreased efficiency. So you definitely want to select a motor that has an appropriate range of RPM at its maximum efficiency, and then gear your car to be conservative so that you can run your car in its most efficient manner. Now, of course, the most efficient motors that you can get out there are in-hub motors. So the other motors that you saw are essentially a spindle design where you put a drive gear on there and you put a sprocket on your wheel, and then you have a chain or a belt that goes and drives that. And so it converts a very high RPM into a lower RPM on your car, on your wheel. On a hub motor, it's essentially made it to your drive wheel. Essentially, there's no gear between the two, and it just sort of mates, bolts on, and then it drives the wheel. And so that gets you a really high efficiency because you don't have the losses of translation for belts and chain drives, right? The downside to that is cost. Both NGM, if you can buy that used from some folks because they're not in business anymore, or the new Mitsuba hub motors, they're really on the order of 25K, and you know, I can design a solar car that runs well on 25K. So that's a very expensive part. So this is more for advanced cars, and of course you have to be an advanced division in order to run these advanced or cruiser divisions. And so if you want to look for ways to optimize in a future design, then that's certainly a way to go, and a lot of cars gain a lot of efficiency there. Now let's take a look at a motor controller. So motor controllers take the electricity coming in from your batteries and from your array and drives the motor itself. And so we call these pulse width modulation, or PWM controllers. And the idea is that you don't really want to be running a motor at varying voltage, right? They're really designed to run at a particular voltage. But how do you vary the speed? And so there's this concept called pulse width modulation, where the controller, based off of your input, will drive more or less power in its duty cycle. So if you want to run at a slower speed, a motor controller might drive 10% on, fully on, and then 90% fully off. And that would be a lower duty cycle. Whereas if you want to drive faster, you would have a wider pulse of on and a lower pulse of off. And it essentially gets the motor to be working in its efficient way and lets you vary the speed. And so you can see that at a lower duty cycle, you have a lower average voltage. At a higher duty cycle, you'll have a higher average voltage. Of course, you have different controllers based off the type of motor that you have. And so for these brushed motors, or for any two-terminal motors, you might use something like an Alltrax AXE that has the right terminals for, you know, battery coming in, motor going out, the motor positive going out, and then a common ground is typically its arrangement. And then there's some 0 to 5K pot control that allows you to adjust how much of the throttle that you want for that motor. It is programmable, and so you can actually program a curve into its acceleration. So if you have a heavy-handed driver where they want to just like mash on the throttle as to start, you can program the Alltrax AXE to prevent the driver from being able to essentially spin its wheels and take off, you can actually throttle that so that it can have a gradual acceleration, which is really the way to optimize your energy use for a solar car. With regard to a brushless motor or a three-phase motor, you might go with a Sevcon. You can see there are 3 motor terminals plus your battery in and out, or sorry, battery positive and negative terminals. And so that would be a way to drive those 3-phase motors. One of the cautions that I would have with Sevcon and with a lot of these type of 3-phase motor controllers is that it's got a lot of safety interlocks. It's meant for use on like forklifts and things like that, golf carts. And so there are safety interlocks for whether or not the driver is present, whether or not you're pressing on the brake. And you might have to do some weird control wiring to sort of bypass all that. I know that when we used that in the Walnut Solar car, we had essentially a power on sequence, right? You had to turn these switches on, and then you had to disconnect or you have to unengage the disconnects, and then you're able to go. And if you didn't do it in the right place, you'd have to turn everything off and start over again. So something of caution, but you know, it worked just fine once you knew how to do it. Finally, let's take a look at other electrical components and some safety issues. So we separate our electrical systems into what we call the main electrical system, or propulsion, the stuff that makes your car move, and your secondary electrical system, or we also call it the supplemental system that runs everything else. And so for your main electrical system, some of the key considerations is you want to use the right wire for the job. You got to look at how much current am I actually going to be using in the car, and make sure that I have the wire to support that. You want to have disconnect switches that are designed for DC, so it can actually break the arc of break the current, so it doesn't arc improperly. And then you have to have the right fuse, and we'll talk more about disconnect switches and fuses next. But on the secondary system, essentially, if you're not using it to drive the car, let's say the motor and motor controller and the raise system, everything else gets to be put into a secondary electrical system for which you have a secondary battery or a supplemental battery that you can charge and discharge. And we let you use that for lights, horn, fans, telemetry, if you can isolate the circuit from your main propulsion system. You can really power all your accessory devices without having to use solar power to deal with that. So let's talk a bit more about disconnect switches and fuses. We require that you use disconnect switches to disconnect your motor from your system and your array from the system. So basically, you don't want a runaway car, so you want to be able to quickly disconnect the motor from your system. And then if you're working on your electrical system, or if you have some type of short somewhere, you want to disconnect the charging coming in from your array. So we require a push-pull type of system, so you can quickly just push the disconnect down. And so one of the common switches that support that is an Albright ED250. It's rated for the appropriate voltage. You can see that there's a rating for 48 volts and 96 volts DC, not AC. That's the important part. And then it has the appropriate load, 400 amps. Now, we say, hey, you know, a lot of teams use these disconnect switches because that's what we require. But new for 2021 is the option to use relays. And the idea is that you have a control coil that goes, if I've got voltage across that control coil, then I will let the current pass through the main lugs of the circuit. If I break that, if I go 0 volts, then it will break the connection. And so that gives you a lot more freedom in terms of your circuit design, because you can put a 12-volt switch on your driver compartment, push-pull, of course, and that will then relay the control to the relay to break it, in the back. Typically, you would have all your high voltage batteries, your motor controller, even your power trackers in one, small location, and then you can then run all your wiring locally instead of bring high voltage cabling into your driver compartment, and then bring it back out again. And so that is certainly a great option for you, and we'll have another webinar that goes into details about how you design your car using relays. Finally, to talk about fuses, we want to make sure that you get the appropriate rated ones, just like in disconnect switches, that you have their appropriate rating for DC and for system voltage. And then we do change the rules to allow for any speed fuse. You don't need a fast flow or a very fast flow fuse there. Finally, we've got a requirement to indicate when your supplemental battery is of low voltage. The idea is, sure, we give you the ability to power all your auxiliary systems using a supplemental battery, but it's not being charged by the solar car, right? And so because there are some critical systems like lights and horns that are run using that supplemental system, we require an audible alarm to tell you, hey, my supplemental battery is running low, I better change it out. And so here's a particular option for you to create your own little circuit for low voltage indicator, but a lot of teams have other ways of doing that as well. And then I'll conclude my presentation with a bit of gotchas. Things that we have seen in solar cars that you should pay attention to in your construction so that you don't come to the race unprepared. One of the things that we've seen very often is that the battery terminals or connections, high voltage connections, aren't properly secured. And we added a rule this year to require locking washers on those connections. The idea is, it's not that when you put on the connector, you didn't tighten it down. That could happen. But most of the time, as you run the car, there's some vibrations that may cause things to loosen. And so, we want you to make sure that you tighten it down with locking washers to make sure that it doesn't vibrate out, or else you start losing some energy due to heat from that loose cabling, and it could cause a fire. We believe that that's one cause of a fire that happened in a recent race. Another thing to consider is grounding to the frame, either by you working on the car after it's been wired up. There might be some nicks in the wire, or maybe even there are some components that aren't properly isolated, like there's some grounding to the frame of the hardware. You could ground your main electrical circuit onto the frame, and we don't allow that. And so something you want to be testing as we go along. There is a question coming in. The question is, should we use different gauges of wire for different components of the primary electrical system? The answer really is yes, you can use different gauges of wire based off of different components, but you have to consider what's in the circuit. So typically, a lot of components are wired in series with one another, and you have to, if you're wiring those components in series, make sure that the wiring is able to support all the components within that circuit in series. Now, if you have a lot of devices wired in parallel, you certainly can look and say, oh, well, I've got, let's talk about the array, right? The array tends to be high voltage but low current, and you get a bunch of them in parallel. And so you would see thinner wire connecting your array to the power trackers than you would do coming out of the power trackers into your battery. And so that is certainly, you don't want to have to use the same gauge wire everywhere in your primary electrical system. As we talk about that, we do see situations where, as you design the car, you run some thinner wire than what you would expect for current. And so you want to make sure that you analyze how much current you intend to drive, especially for the motor and for the battery, and size them appropriately. And then, of course, your disconnects and fuses also incorrectly rated is something we see all the time. For the secondary system, we see a lot of grounding the frame there too, and especially because of telemetry, right? You may end up connecting some things that would ground to either the frame or to the main electrical system. And so you want to make sure that you have proper isolation between the two, or if in case of a telemetry system, that you explain to us your electrical design that says, we plan to have some type of common ground there, but we won't be charging it via the telemetry system. And so you can explain that to us as well. Brake reliability is another thing. There, if you put in brake switches, sometimes they're fairly light switches, and depending on their placement and how much they bend, there might be concerns there in terms of its reliability. And then a lot of loose connections, especially on crimp connectors, where if you crimp it and you don't solder that crimp connection, it can break there. And so this is sort of a quick look at an electrical system. We'll go into details in further webinars, but I'll open up for questions, including one that just came in. We mentioned that solar cars with a curved solar array could have power loss when wired in series. If an array was divided into a smaller section, would an MPPT be needed for each section? And yes, that's the thing. If you divide your solar array into different zones, those different zones would be each individually wired into a power tracker, and then you would wire the outputs of those power trackers in parallel into your battery system. That's the way you would design it. And of course, thank you, Will, for correcting me in terms of the explanation of the lithium battery. As he said, C is a measure of how quickly a battery is discharged relative to its total capacity, and discharging at a rate of 1 C means that all of your battery capacity is discharged in exactly 1 hour. So thank you for clarifying that for me. I'll open it up further to any other questions. All right, hearing none, I will move on. The fun part of building a solar car is the ability to make the engineering decisions, right, based off of the different criteria that you put together, the different trade-offs that you have to consider. You can't make a perfect car. You may gain efficiency from lowering weight, but then you have maybe less battery capacity because you put less weight in your car. So before we start talking about telemetry, I want to show you how Raisbeck Aviation High School weighed some of their engineering decisions.
Immediately after our return from Texas, after the car was safe and secured in Seattle, we hosted a team gathering to celebrate and reflect. We recorded the insights and experiences of many different team members before they left for college and thanked them for all their hard work. The class of 2019 formed the Green Energy team, and they finished their last year very strong. We were eager to keep their momentum going. One of the first questions we addressed was whether to build a new car for the 2020 challenge or to improve upon the car we had previously built. We are very proud of that car, but there are so many places where we could improve. Our team was always up for a challenge, and that's why we chose to build a new car for the 2020 challenge. planning to break our own record. Here's our story.
Now that we had the luxury of a 2019 car as a failsafe, there was much more space to explore, prototype, and research potential improvements. Last year's experience and reflection led us to a few core design philosophies that we agreed upon very early in the stages of the car. The first was that anyone on the team with a license could drive the car at the competition. The second was an emphasis on efficiency. There were two main body styles that we considered: a catamaran style, or a single central body. Our research phase approached these designs with an eye on aerodynamic efficiency, stability, and ease of manufacturing. To accomplish the first value of accommodating all team members, our car would need to adjust to the driver's height and proportions. The mock pit was really our groundwork to reach that value. It was simple and cheap enough to change our prototype quickly, but having a physical model was incredibly useful for ensuring legality within the rules and feasibility to manufacture. Our core value of improved efficiency meant we needed to spend more time researching and crafting the aerodynamics of our design. For a while, we had been intrigued by the possibility of computational fluid dynamics as a design tool. So during the research phases, we tapped into our network for advice from our Boeing engineers. They encouraged us to utilize the tools at our disposal, but always validate the computer output with practical testing and previous research. Our network of engineers also helped us investigate different building materials and techniques. We learned a lot about what goes into the design of a composite structure, and were fortunate to get our hands on quite a bit of it. This early part of the year was also full of learning general engineering skills. We introduced many new students to electronic design, welding, machining, CAD, and programming. We want students to find the area that excites them the most, and giving members the freedom to work on any project is an important method of letting them explore. Our research phase ended with a few key deliberations. We chose the catamaran design because it offered greater stability and ease of manufacturing. While there was some promise of the single body, its main fault was the difficulty of quickly and safely getting the driver out without stepping on the solar array surrounding them.
Our design looks a lot different. We've learned so much and we're excited to try something a bit new this year. We've changed to a 4-wheel symmetrical drivetrain and brought down the solar panels to shoulder height. The added wheel forced us to rethink our steering column, as now we must turn 2 front wheels rather than just one to meet the competition's steering radius regulations. Our solution is an optimally placed bar linkage connecting the 2 front wheel suspension systems that allow us to implement an Ackerman steering system to meet the competition requirement. Bringing the solar array down to shoulder height has the trade-off of creating shading from the cockpit. If left unchecked, shading can significantly lower our power, dissipating current as heat, which could lead to damaged cells or even fires on the car. We had to redesign the solar array to fit the shade of the canopy and provide connection points for current to bypass any shaded cell. Something we underestimated last year was the number of wires that accumulated in our car. Messy wiring not only slows down our maintenance of the car, but is also dangerous. This year we spent a lot of time planning our wiring by using 2D CAD to create electrical schematics. We've used these schematics to build a central electrical board that is equipped with most of all of our connections, relays, capacitors, etc. We've also looked to improve the safety of the car by isolating high voltage to a smaller section, and no high voltage wires will pass through the driver's cockpit. Another one of our greatest efforts this year was a complete redesign of the telemetry system, using a custom Arduino instead of last year's approach, which used an off-the-shelf product. Instead of transmitting data over a cellular network this year, we are now sending it through a radio frequency and logging it at our base camp. As this is an endurance race, we have to look at reducing drag as much as possible. This is important because drag increases by velocity squared, and the power needed to overcome drag force is proportional to the cube of the velocity. This means that if we go twice as fast, the drag forces would quadruple. To reduce our drag, we have been designing an aerodynamic shell for the car to encase the entirety of all the systems using different computational flow dynamic software, which will make a more aerodynamic design.
This year, our team has been working to redesign our telemetry and data acquisition system. We are collecting upwards of 70 data points all throughout the car, including values such as motor temperature, solar panel current, battery voltage, etc. We are now experimenting with the best method to send those data points from the car to a strategist computer off-field. We so far have tested using Arduino and radio frequency, Raspberry Pi with Python script. We have also experimented with sending the data with internet and with no internet connection. Our goal is to create a system that a strategist could use to visualize all of our data points and then communicate back to the driver about what they should do to maximize energy efficiency and speed of the car throughout the race so that we can drive as consistently and predictably as possible.
We started our fundraising journey with a team-directed letter writing campaign. In order to broadcast our voice to a wider audience, we used our website to keep our supporters informed about the progress of our team. Collectively, we produced monthly blogs that highlighted the accomplishments and milestones of our team. During the year, we organized multiple events and presented our team's mission to the Raisbeck Aviation High School PTSA auction, the Highline School District, T0 Racing, and the Royal Aeronautical Society's Seattle chapter.
As the COVID-19 outbreak emerged, Washington State was the first to shut down all schools and non-essential businesses in the nation. In anticipation of distance learning, we packed everything in our school workshop and transported to our mentor Dr. Sumay's workshop until further notice. The team adjusted remotely while King County was in Phase 1. We quickly discovered that structural progress on the car was not possible as members were isolated from each other and the chassis. In response, our focus shifted to independent projects of electronic and telemetry systems. Weekly, we continued team Zoom meetings. This gives us a space to reconnect with teammates, share our progress, setbacks, questions, and future projections. While we were isolated from each other, the key to continuing progress from home was maintaining efficient group communication. When King County proceeded to Phase 2, the team could finally arrange to meet in small groups to work on the car. There was a huge learning curve as we learned how to social distance, wear face masks, frequently wash our hands, wipe equipment down, and work in ventilated workspaces. We've made great progress, but as we remain in Stage 2, we still do not have access to our school workshop. So, we intend to continue meeting up at Dr. Sumay's workshop as much as we can to continue making progress on the car.
So as you can tell, telemetry is one of the keys to the Raisbeck Aviation design, and they're collecting upwards to 70 data points in their system. The Okemos Solar Racing Club also gave a lot of attention to their telemetry in their design. I was impressed with just the way that they not only collected information but displayed it for just easier digesting by the strategy team, and even having the ability to communicate with the driver through that system. And so I would like to introduce Will Jones and Eric Andrzejczyk, former and current captains of the Okemos Solar Racing Club, to talk to you a bit more about their design.
All right, good afternoon, everyone. Looks like Eric's getting the slides pulled up here. So I'll introduce myself first. My name is Will Jones. I'm a sophomore at the University of Michigan. I'm studying mechanical engineering. You'll note I gave another presentation about a month ago, and it said computer science. So actually, I just changed my major, trying to keep things straight. As was mentioned, I'm the captain and the founder of the Okemos Solar Racing Club. Currently, I'm actually the systems integration lead for the University of Michigan Super Mileage team, and I'm also excited to announce that this summer I'll be the assistant race director. And then, Eric, do you want to go ahead?
And I am Eric Andrzejczyk. I am a senior at Okemos High School. I'm currently the captain of our solar car team. I've participated in a lot of programming and computer science competitions, including the North American International Cybersecurity Summit, which was a big cybersecurity event where I placed first, as well as some state and national coding competitions.
All right, real quick, Okemos, we're right in the middle of the mitten, about 15 minutes outside of our capital Lansing. So just to speak real quick on the success that we had when we raced 2019, the last race to have occurred was the first time Okemos had ever competed at the Solar Car Challenge. Our team finished second place overall. We won the Lockheed Martin Engineering Excellence Award. And while we're here today, we also won an award for our telemetry system. So real quick, I always just like to show this. This is just a cool clip of our car. This was a couple of days before we left. So now we can dive more here into the telemetry. And I know a lot of people, actually when we won the award, my mom was at the competition and it was announced that we'd won the Telemetry Systems Award. And that award is actually given before the competition takes place. And my mom wasn't familiar with what a telemetry system was. So essentially what telemetry does is it kind of gives you the heart rate of the car. And you're able to take the key vital information and, understand how your car is performing. And hopefully you're able to take that data and, just as an athlete can look at their heart rate and know whether they can push harder or maybe need to ease up. You can know whether to drive your car faster or drive your car slower. I guess that's all there really is to it. And before we dive in too deep here, one thing, and I always feel like I need to give this warning, is you can have an awesome car and be super competitive without a telemetry system. And having a car that's reliable and is able to run the whole time is gonna result in you placing higher and probably having an overall more enjoyable experience than having an awesome telemetry system and maybe struggling to get through scrutineering or not being reliable during the race. And I'm not warning you and saying don't do it, but just make sure that you have a reliable car before you start spending time on this telemetry system. So why would you want a telemetry system? What is the benefit of it? And I think the first thing that always pops into mind is obviously the strategy and being able to push the car to its absolute maximum and not leaving anything on the table or maybe driving too fast in the morning, having to slow down in the afternoon. But I think another super important thing to consider and something that was definitely experienced during the Solar Car Challenge is that the car that's able to drive reliably is going to be super competitive. And if you have a telemetry system, you'll be able to spot issues before they actually arise. And if you have temperature sensors and that kind of thing, and you see the motor's overheating, the panels are too hot, you can solve that before it becomes a unsolvable issue or something that's going to take a lot of time and potentially money to solve. Another thing that's super beneficial is being able to communicate well with your driver, and that was a big benefit of our system, is clear communication. It can be difficult, especially you're going around the track. There's lots of other cars. Your car's probably loud. There's lots of wind noise. And something I think that's also exciting about it is it's a challenge. It's something for people to do. If you already have a car and it's good and it's competitive, this is something that every single car can have added on, and something that lots of people can work on, and it's just a great next step for teams. So what are the data points that you really want to look at? And for us, we kind of decided that there were three things for our initial system that we really want to focus on. The first one is voltage, and I'll show a slide next and why voltage is important. The second one is car speed, and obviously this is pretty straightforward. You're able to monitor your driver, make sure they're not driving too fast or potentially too slow. You're also able to see how your car is performing, and then the driver communication, like I already mentioned. So why is voltage important? And I think voltage is something that can be kind of confusing because I think a lot of people think batteries maybe more in terms of a gas tank rather than how batteries should be thought of. And in a gas tank, if your tank is 100% full, then there's all the gas in it. And when it's empty, there's no gas left. But a battery is a little bit different. So as you can see in this example here, a fully charged 48-volt battery, and I think this chart might not be totally accurate, but it's all good for this example, would sit at about 51 volts. And when it's fully discharged, rather than sitting at 0 volts, it's sitting at about 46. So if you're able in real time to see what your battery voltage is, you'll be able to accurately determine how much gas is left in the solar car. So real quick, I'm going to give a talk on strategy, and this is something, the math presented here is something I wish I had been able to see before competition and kind of had to figure out on my own. And I believe these slides will hopefully, we'll try and make them available because there's a lot of math here and it probably takes a minute to actually comprehend, and I'm going to speed through this a little bit. But basically what we figured out was our array didn't tilt, but on a sunny summer day in Texas, you get about 6 1/4 of the rated capacity of the array. So if you have a 1500 watt array, you would expect to collect about 9,400 watt hours. So using data and we're going to talk about this device in a second, but we're essentially able to determine our watt hours per mile, or a direct correlation to that would be our miles per gallon. So we know we're collecting about 9,400 watt hours, and so we know we're collecting about, call this 9.3 gallons of gas, and we use about 0.1 gallons of gas, 100 watt hours to go 1 mile. So from this, we're able to determine what your average speed should actually be. And if we go to the next slide here, just to show that I'm not making numbers up here and how accurate this can really be. So our array in 2019, its rated capacity was 1,475 watts. So we collected, or we were expected to collect about, 9.2 kilowatt hours per day, or somewhere around 37,000 watt hours for the duration of the 4-day competition. And going in, we did a fair bit of testing, and the number that we were bouncing around was about 83 watt hours per mile, and that's about where we thought our car would fit. So from this, we're able to estimate we could do about 444 miles, and our actual distance traveled during the Solar Car Challenge was 461 miles. As you can see, this turned out pretty good. One thing here that makes my numbers a little bit better is we don't consider the initial capacity. And the other thing too, and William was talking about this, that Pukert number is battery efficiency is not 100%. So if you put in 9.2 kilowatt hours, realistically, you're not going to get that much energy out. So telemetry systems, are awesome, but essentially what we figured out is if you have these 3 devices right here, walkie-talkie, and this was the shunt I was talking about. This is a super important data collection tool that I think every car needs to have, just because it's accurate, it's super inexpensive, and we found it to be very reliable. And then just a GPS speedometer. Essentially, from these 3 devices, you'll be able to determine your watt hours per mile, your total distance traveled, and it's not going to have the awesome telemetry data display that Eric's about to show off and that we are super proud of, but it's going to be able to give you the data that you need in order to keep your car running around the track and driving with a strategy that results in a competitive style of racing. All right, so real quick, and we've been running with FAQ. If anyone has any questions, go ahead and ask. If not, Eric is going to dive deep into how our system actually worked.
All right, so I guess I'll just start then. Thanks, Will. So going off of what he was saying about that bare bones telemetry system, I'm going to go over our system from last year first. Oh, here's a question coming in. Yeah, I'll go over all of that in the coming slides here. That's all going to be stuff that I cover. So our old system, okay, Will, do you want to go over the watt hours per mile there?
So the question is, how does the watt hour per mile translate to a continuous power consumption in watts?
So that's relatively straightforward here. You just multiply. So say you're getting 100 watt hours per mile and you're averaging 20 miles an hour. You would just multiply the two numbers together, so 100 watt-hours per mile times 20 miles an hour, and that would be 2,000 watts of continuous power drain on your system.
All right, so going back here, this old system, this is the one we used last year. I think this is a really good starting point for a team looking to get into a more advanced telemetry system and to try to transfer from what Will was going over with just the walkie-talkies and a speedometer type thing to try to really start on a telemetry system. This is a good spot. This is pretty bare bones for a telemetry system. It's just logging voltage, speed, lap time, distance, and then we have that messaging functionality as well. Then this slide will be made available so you can see all our demos down there. There's a picture of what we started with. We made a lot of changes to the system during the actual race as we figured out what was actually important. But the gist of it is you have an Arduino recording data passing to a Raspberry Pi that's also recording some other data, sending it to our servers, to a database, and then to all our devices. So this is kind of the display that the driver saw. We had it on an iPad connected to a Wi-Fi hotspot in the car running on someone's phone. So the driver can really quickly glance at it and see their speed and know what target speed to be running at, which is something that the analysts back at the pit will be radioing to them to tell them to aim for. And then they can also see the cautions on the right in the bottom there and the messages from the home base there. So that was very helpful in that when our judge would tell us there's a caution on a specific turn, we can type into our phone and hit send, and on the driver's display here, it'll flash really brightly and catch their attention and show where a specific caution is, and then we will clear that caution when it's gone. So if the driver's unsure of something or they see an incident up ahead, they can know whether or not they need to slow down for that or not, which helps avoid penalties. And there's also lots of other data that they can look at, but that's really more for the pit crew. So in the car, the iPad display we had there sat right above that wooden box you see the arrow pointing towards. We kept it plugged into our supplemental system. So our supplemental system did have some power drain last year, which is something we're trying to work out for our future systems, but that was also partially because the iPad was pretty old. So here is what the pit crew would see then. We had a TV sitting in the pit, and so all of the members in our tent could see the car's speed in real time, all the messages, cautions, and all that data on the right. And that really made things more interesting for the team, as well as providing useful information that we could constantly be watching and keeping track of and knowing kind of how we should be running our car and what speeds to tell the driver to aim for. So the system laid out here, we'll start with the Arduino. That is, in our old system at least, that was only being used to get analog data from the main power supply and pass the voltages to the Raspberry Pi. So we just had a simple voltage divider that I'll show in a little bit that was just logging the data or logging the voltage from the main system out of 5 volts after being divided. And then over the serial communication port plugged into the Raspberry Pi on USB, that was sending the voltage data it was gathering as fast as it could. And then that Raspberry Pi was plugged in from the supplemental power source. So through USB, it was also powering the Arduino. And the Raspberry Pi there, in addition to collecting the Arduino's system battery information, it also was hooked up to a Hall effect sensor. So that's like the one on your bike wheel if you have a bike computer, keeping track of your speed there. And that was recording our speed as well as our distance. All that data was getting packaged and sent over the Wi-Fi hotspot in our car to our server, which was updating our database. And then that database only kept track of the real-time data. We weren't storing old data as well. And that was updating all of our displays in real time. So this old system, we used an Arduino Uno, and that's basically, it was solely used for that purpose, so fairly straightforward with it. The Raspberry Pi, this is it on our car. Actually, initially our Raspberry Pi was inside a little case underneath the hood of our car, kind of out of the way, but we found that in the Texas heat and race day, it was actually constantly getting overheated and would just shut itself down. So by like the second day of racing, we had zip tied it to the hood of our car just to get some airflow going over it, which I wouldn't recommend as your like optimal solution, but it did work for us. So you can see the 3 wires going into the GPIO pins on the Pi there. Those are all coming from the Hall effect sensor. The USB on the right side, that is the serial communications to our Arduino, and then it was just powered with our supplemental system, and that was all just being uploaded to the phone running our hotspot. We used Google Cloud for all of our database and server. So Google Cloud, when you sign up for an account, you get $300 of free credit, and then if you need more, you can basically just fill out a form and hit submit, and they granted us another $1,000 in credits. So we didn't have to worry about going over any server budgets there. But our Google App Engine was running a Python server, and that was collecting our data, doing whatever it needed to it, and then pushing it to Firebase real-time database, which could update all of our devices in real time. So here's what that Firebase real-time database looked like. So you can see some of the data we were collecting there. Basically everything went through that, and we just recorded, as I was saying, just the real-time data. The Firebase real-time database had like a 5 GB storage cap, so it wasn't optimal to store all of our previous data in it, plus it could slow it down a little bit. So we just had it writing over old data points as they came in. Then Google Cloud Server was hosting, as well as receiving the data, it also hosted those web pages you saw. So the iPad's display, that was just a web page running in full screen on the iPad. And the pit crew display you saw was also a web page, and the TV had a Raspberry Pi in the back of it that was just displaying a web page on full screen on the Pi that would automatically just open on boot. So all of that was hosted through Google Cloud as well. And then on our Solar Car Club webpage, which is hosted on Weebly, we had embedded a little HTML page into our Weebly site that just grabbed the data real time from Firebase and could display it there, which was really easy because it's all just a static web page. So that didn't require any extra workarounds from the server side. Voltage, as I was saying, this was really straightforward with an Arduino. This was the code we used. It just is basically grabbing that analog port, reading the value, and then you can see down there we are doing some math to kind of figure out what the voltage is after being divided, because we had it out of a smaller voltage because as we learned the hard way, our Arduino cannot read 50 volts. Yeah, we lost an Arduino to that, but voltage divider does the trick, and here's what that voltage divider kind of looks like. It's just 2 resistors on either side of the analog reading, and yeah. So then the speed and distance, that was done with the Hall effect sensor. If you've ever had a bike computer or anything, that's how that most likely works as well. It'll have a magnet on the spoke and then a sensor on another part of your bike, and every time the magnet passes the sensor, it gets a reading. So that seemed straightforward and simple, and it is relatively easy to do. Just have to know like the circumference of your wheel or whatever. And our Raspberry Pi could grab that data point every time it passed and know the elapsed time between the last time the magnet hit it and the current magnet hit, and using the amount of time that passed and the circumference of the wheel, you can get things like speed and distance, and all of that information was then uploaded to our servers, and we could keep track of everything like that. This is straightforward and simple, but we had some issues where the sensor would get bumped and fall, or turn slightly and miss a magnet reading, and that can mess up your data. But for a simple system, it's not bad, especially if you're not looking to implement everything to the cloud and stuff. If you want to just make this something that your driver can see, you can totally just buy an off-the-shelf bike computer for this. Lap times, that was something that we found was useful for pacing after the first day. Again, going into the challenge, it was hard to know what all we really wanted to see. So like that communication information and cautions, we didn't know that that was going to be something we wanted. As well as lap time, that was hard. But after taking a look at the Solar Car Challenges website, they very helpfully keep track of how many laps your car has done. And so on like the second day of the challenge, I was there with my computer taking apart how their tracking system worked, and found that it was essentially just a pretty simple API that I could parse in Python. So I implemented this code right here onto our server, and it could just find where the word Okemos was on the page and grab our data from that. So we knew how many laps we had done, lap times, penalties, everything. And then we had that displayed on our pit crew screen as well. So if our car would make a lap and that number didn't increase, we knew to tell our judge, hey, you got that lap, right? And so that was helpful, as well as knowing how many penalties we had and everything. Messaging here, this was also something built in the hotel room between the first and second days. I essentially, just because it's a really simple Python server running the bulk of everything, I just added basically some webhooks in to accept like messages and warnings and cautions and all that. And then from your phone, you can just go on to those web pages, and I added shortened links of those if you want to try them out on your own. They just send post requests of your message straight to our server, which just updates the database and displays it on everything. So it's pretty straightforward. This year we have a Twilio phone number purchased, and so that allows us to tie in a phone number to our server. So now you can text a specific number and that'll display the warning on the car. It just makes things a little easier for everybody, but yeah, this is totally doable and really straightforward as well. So the costs of this system, this is kind of your bare bones system, the one we used last year, a good first step for looking at telemetry. Raspberry Pi is $35. You could also do what we did with the Raspberry Pi with an Arduino and a Wi-Fi module, which would bring that price even further down. Arduino, $8. You can probably find some for even cheaper. Hall effect sensors and magnets, next to nothing. Voltage dividers, that was just resistors. The iPad and the TV were the most expensive parts. We just used an old iPad that I had laying around, and you can also find them on like eBay or a Fire tablet for like $30. TV monitor that was donated to us. Then the server and database, I talked about that with Google App Engine. And the Wi-Fi hotspot, we used just the driver's phone running a Wi-Fi hotspot, but we also found that our local library actually has Wi-Fi hotspots that you can basically just borrow. So we spent around $10 on that whole system, which was pretty remarkable. And so off of that system, we decided that we wanted to make that public this year. So if you want to check out our Solar Car team's GitHub page, you can see all of that code for yourself. And if you want to try to like kind of copy our system or model your own off of it or whatever, you're welcome to do that with our code. I did write all of that code the week before we left for Texas, so there is minimal to no commenting in it, and it's not very well documented. So if you do have any issues or questions with the code or how to set it up, feel free to reach out to me. I also put in our GitHub page kind of a walkthrough on how to set it up on Google App Engine. So if that's something you're interested in doing, feel free to check that out. Our link is right there, and we'll also have this later. So moving forward, this year we have some pretty ambitious plans to one-up our telemetry system from last year. So going back to the baseline though, the three main pieces to your good telemetry system would be gathering that data, all your sensors and everything, communication, so transmitting that data back and forth, and analyzing that data so you can tell your driver how fast to go. So when talking about data, more is generally better. And I say generally because one of the things that we had people learning telemetry doing, so something really easy for them to learn and to practice on, was adding temperature sensors to our car. Just a simple temperature sensor in an Arduino, and that was really easy for them to get the hang of. So I came from helping the electrical team to come check in on the telemetry system one time, and I found that they had used an entire pack of like 20 temperature sensors, and I was asking them where all the data points were, and someone had put a temperature sensor inside the driver's water bottle so that we could keep track of the driver's water bottle temperature remotely. And so when you're looking at analyzing how your car is running and keeping track of how to keep it running most efficiently, in general, it's good to have a lot of data points, but you have to keep in mind what's actually practical for your car. I don't think that the temperature of your driver's water is going to be system critical. I could be wrong. I don't know. Then about that communication. So the caution and the comms on the screen, I strongly recommend that. That was really helpful. You also need to make sure that that transmission system is quick. So in ours, we had under half a second of latency. We're trying to get that down to under a quarter second this year. And that was over cellular internet. So you can add in reliability there with trying to implement like LoRa antennas as well. Two systems is good for redundancy, or you might just want to simplify things with one, however you do it. And then analyzing the data. So you really want to look at your data, and it's really helpful to run your car in full practices before you take it to Texas. So driving it around where you can near you with everything implemented, including your telemetry, you can really start to get an idea of what the data is telling you and how to use that data to run your car efficiently before you take it to Texas. So watching that data and aiming to keep your watt hours per mile at your targeted amount is something to really practice and get good at. And then you also have to keep in mind that this is a race. And so on the last race day, you don't want to be holding your optimal efficiency speeds there. You got to really remember to kick it into gear and burn all your battery while you can. So our new system this year, we are adding amp draw from the motor, which is really something we should have had last year, but we were under a bit of a time crunch. So amp draw, temperature readings for various different components of the car, wattage output from the panels. We want to try to add adaptive cruise control so that we can just use the equations Will was talking about earlier and kind of use all the sensor data to automatically control our car's speed. And then the Raspberry Pi last year, we did run into some issues with, as I was saying, with overheating, as well as a lot of power draw. That thing was drawing the supplemental system a lot, and that supplemental battery died every time we needed to do a driver swap. So running purely on SBCs like an Arduino would be a good idea. The code might not be as easy to get some newer people on your team writing. students that haven't done a lot of coding before might struggle more with writing the Arduino version of C++ rather than starting with Python on a Raspberry Pi. So what we are doing is we're letting the newer students work on our server code, which runs Python, and then other students doing the Arduino code. With an Arduino, you do get faster boot time, less current draw, and it's more reliable in general than the Raspberry Pi. You don't have random crashes as much, and it's not running a whole operating system underneath, so there's a lot less things that can go wrong. We also wanted to add GPS this year, as I was mentioning, with all the hiccups we had with the Hall effect sensor and issues reading that data. We thought it was important to add GPS so we could watch the speed of our car and distance, as well as, I think it would be pretty cool if on our pit cruise TV, we had like a map of our car and showing where it was on the track. I know when we were coming to get our car last year, I had my phone out watching kind of the distance of our car to estimate where it was. And I know William was saying, oh, that's cool. Do you guys like have a map to see where the car was? And I was like, oh, we don't, but that would be really cool. So obviously we have to add that this year. And then live graphs. So last year we weren't keeping any of the data that we had. We were just using the current data. This year we're going to try to store all that data so that we can graph it live and analyze it later, rather than just having Will's dad sitting in the back of the tent writing it down on a spreadsheet on his laptop. So talking about motor draw, some motor controllers may have a plug and play way of reading draw. Ours, I couldn't figure out if it did. So basically we're just trying to implement a shunt and read that on an Arduino. There's some pictures of kind of how that works here. It is fairly straightforward once you find a shunt that works, but that's really hard to do because not a lot of shunts are compatible with such high amperages while also being able to hook up with an Arduino. So we've been struggling to find one, but the actual implementation of it isn't terribly difficult, and I've linked a website there for people to check out later. Temperature readings, as I was saying, this is something really great to have the new students on your team that are interested in telemetry doing. TMP 36 temperature sensors, you can buy a huge pack of them for next to nothing. And so when the kid plugs it in backwards and it overheats and stops working, it's not a huge deal. And they're super tiny, they're waterproof, they're durable, they have a large range in what they can read, and they're fairly accurate. They're not the most precise temperature sensors on the market, but they do their job well enough that you get a general idea. You just have to make sure that you calibrate it. They can be slightly off, especially if you're trying to follow an online tutorial on how to install it. They have pre-calibrated numbers that you can use, but we found that those were not quite what we wanted. So some testing on your own is helpful there. Then talking about solar panel wattage, we do use a midnight charge controller on our car, as William was talking about earlier, as a charge controller option. It has that screen right on it. So one of the things I've been playing with this year is trying to figure out how to grab the data off of that charge controller. We purchased a Whizbang Junior, which is sold by Midnight Solar, and you're able to get some readings off of that. There's also on the Midnight, at least that we use, there's a little aux port down at the bottom that is outputting some data. You just have to really kind of play with that to figure out how to read it. I couldn't find a great tutorial on how to do that. If worse comes to worse, you can always set up a camera pointed at your Midnight and read the text off of image recognition or something. But yeah, okay, so battery voltage, we're using the same voltage divider kind of thing as last year. Not really much has changed here. We have done a lot of testing with it, and actually one of the really cool things with the voltage divider is rather than the commercial shunt that we were using or the data coming in on the charge controller, we found that our voltage divider that we calibrated ourselves and hooked up directly onto our batteries was giving us better readings than either of the two things. So if that's something that's important, getting those extra decimal places of accuracy and precision, then that's definitely something to look at. GPS, there are lots of Arduino GPS modules out there. Some of them can be relatively expensive. Some of them are cheap. You kind of get what you pay for with them. We settled for one around $40. So basically they just feed latitude and longitude data to your Arduino in real time. And then using the math and the equations I have down there, that's kind of how you can use those latitude and longitude coordinates to find distances between things, and using distances and time you can get speed as well, and you can also transmit those GPS points back to your pit crew to display on a map. And there are also some cool things you can do with GPS points and some third-party mapping systems. If you look at some of the maps designed for runners or bikers, some of them actually include APIs where you can take GPS coordinates and they'll tell you the incline of the hill at that particular spot. Ooh. So if you want to anticipate hills in your road race, you can use GPS coordinates to map all of the hills in advance and know how to plan your road race better. Cellular and LoRa. So Arduino Wi-Fi modules are something that we're going to use this year instead of a Raspberry Pi with built-in Wi-Fi, but that is an option for you as well. We just had them connect to the driver's phone or hotspot, but then we're also implementing LoRa antennas this year. In talking to other teams that have implemented them in the past, most teams seem to all agree that they do work on the entire track race. No one has had very many issues with them dropping signal, so that's good. A lot of our system, though, does run on cloud servers, so it's not ideal for us to use LoRa antennas because our cloud systems have such minimal latency as is. So actually what our LoRa system is going to do is just use an Arduino with the LoRa plugged in on the right there, and then have a Raspberry Pi running LoRa back in our home base. And that Raspberry Pi is just going to be taking the LoRa stream of data and uploading it to our cloud servers just as a redundancy in case something happens on the Pi and we lose cellular connection to it. But other teams may rely more on LoRa and less on the cellular model if they're not running as much on the cloud. That does get you better transfer speeds. So logging and predictive modeling, this is where we start to get into the math and the computation of our telemetry system this year. We want to record our telemetry data. We don't want to just throw the data out so we can just use the most real-time things. So we have implemented the Google Sheets API into our server code, and that can log all of your data into Google Sheets. So you can automatically build in formulas and graphing into Google Sheets however you want. And then Google Sheets allows you to embed graphs onto your web pages. So on our pit crew screens, we can see the Google Sheets, whatever data point we want, graph in real time being changed. And we can also look at that at the end of the day to analyze our data. And then because we have all of our data logged, we can run predictions and anticipate what is happening. So for example, we are implementing a weather API this year, and there is a weather hub on top of the Texas Motor Speedway that gives data like temperature and real-time cloud cover information. So we have been pulling from that API real-time cloud cover data, and we can anticipate when the sun's about to get covered up and know if we want to change the speed of our car because of that. We also know on the track with the turns where the hills are and where we want to change our car speed going over track hills. We also know kind of a correlation between data. So when the sun is covered and when we're going downhill, what we can expect our car to do. And that helps us kind of fine tune how we want everything to run. Then kind of eliminating as much human error as possible here. Instead of analyzing our telemetry data like we did last year, we want to try and have everything run automatically. So in our new telemetry system that we're hoping to have for our 2021 race, we are completely eliminating the need for our pit team to watch the data. They still will because it's interesting and because we can double check everything, but we have been working with a open source racing system that you can see here. Let's just screenshot taking from this little like racing simulator. And we are feeding all of our telemetry data points to each car so they can see all of the data in a simulated manner. And then we run an evolutionary training model on it. So we hit go on our simulation and each car kind of just randomly drives with the telemetry data. And one car is going to maybe minimally outperform the others. And so we'll select that car and say, all right, this one used the data better than the rest. So generate a new generation of cars off of this one's usage of the data and run it again. And then all those cars are going to have slightly improved versions of using the telemetry data. And so we can just run this over and over and over again until we have the optimal system. And so it takes into account all of our useful telemetry data and can automatically tell the car what speed to go at. And so knowing what speed to take the car at, we reverse engineered our throttle for our motor controller. And our throttle is essentially just a potentiometer with 5 volts coming through it, just controlling the motor controller like that. So that is something that you can plug into an Arduino and control automatically. So what we're trying to do here is have a button on the dashboard that the driver can push to engage the cruise control. And then if the driver pushes the button again, they can disengage, or as soon as they hit the brake or regenerative braking, it disengages cruise control, whatever. But this speed data then is all processed and given to the Arduino to tell the motor controller what speed to take the motor to or how to push the throttle. And that means that the driver is just steering and braking, and the car is essentially driving itself. And so, I don't know, nothing in the rules says that a human has to be in the car. So hopefully in the future we can just add cameras to track the lines and eliminate like 150 pounds of weight in the car. That would be a good weight reduction, but
No.
yeah.
I
So
see a rule update coming.
yeah. So that's kind of how our AI system is going to try to work. The only downside to that is that running an artificial intelligence model, it doesn't generate an algorithm, it just generates a model. So you can't just take the output from it and use that algorithm on your car on an Arduino. It generates this big, complicated file that only the machine learning system can run. So that means that on our car, we're going to need something more powerful than an Arduino to run that model. So unfortunately, we are most likely going to have to add a Raspberry Pi or some other system like that to process that data real time. And so one of the big challenges we've been trying to work out is getting this system to less than 1/4 of a second latency, because if we want to change the speed of our car as we're going up a hill and it doesn't change until we're halfway up the hill, that's not really doing much more than the driver would then. They know that and they can process that faster. So getting that speed down as much as possible, making it able to run on a lightweight Raspberry Pi, and also not drawing too much power are all challenges that we're currently trying to work out. But the end goal is to have this running on our car and doing everything automatically. So I think that about wraps up what I had to talk about with telemetry. I think I answered the database question. Yeah. So if there are any other questions, either for strategy or implementation of anything.
Gentlemen, I want to thank you. I appreciate what you're doing. I want to commend you for an exciting presentation. Eric, I want you to email me today. We're going to talk about artificial intelligence here because of an idea that I've been mulling around for a while. I think we can move this forward in some form or fashion. I want to thank everyone for tuning into our webinar today, and I want to commend William and Eric and Will for all that you did to make it a success. Our next webinar is scheduled for December 5th, and it's dealing with the importance of the oral presentations. Now remember, this year, you can earn up to 20 laps on your race by doing an outstanding presentation. So this is worth your investment of time. We're also talking about scrapbooks, and then the crucial question of how to prepare and pass scrutineering. This weekend, I'll be publishing our webinar series for the spring. I want to thank y'all for tuning in today, and please address the questions to me, and I'll pass them along to our various discussers today. Y'all have a wonderful Thanksgiving. Stay safe. We want to see you at the 2021 race.